Lasse is visiting, Lasse is a PhD student in Aarhus with Torben Lund, I guess, and you published with Nordic at 3 Tesla layer fMRI before. They used VASO as a structural reference, but not VASO as a kind of functional task. So Lasse has been here for 4 weeks now, and it has been very productive 4 weeks, as you will see. And the purpose of this was to basically find a way or get a feel for how to use Nordic denoising in the weird framework of layer fMRI VASO, where we have more than one contrast, we have a different sequence, and Lasse will talk about that. Yeah, what the considerations were, please. Yeah.
Right. Thank you. And also thank you very much, Dan, for having me here and allowing me to present. So yeah, as Renzo just mentioned, my name is Lasse, and I'm in my 3rd year now in my PhD. And during this secondment here with Renzo for 4 weeks, so this will be like a summary of what we have been doing for the past 4 weeks. And then we also plan to make a blog post with a little bit more details, some extra figures, but this will just be the most important part that I'll present here. And yeah, the theme is Nordic denoising on VASO data. So first, a little bit of background. What is Nordic? It's a PCA-based denoising technique that aims to remove the components from the data that cannot be distinguished from zero mean Gaussian noise. So that would be suppression of thermal noise. And here you can see an example here to the right of what Nordic can kind of do for your images. So this is an example functional image, which is gradient echo bold at 3T and at sub-millimeter resolution. And it has a lot of this salt and pepper thermal noise on top of it. And then here to the right, after denoising, a lot of this seems to have been removed. And the image looks much cleaner. And also this also translates into the time series, where you can see this is from an example voxel where after denoising, this paradigm modulation here, which was a block design in this case, becomes much more clear even in the raw time series after denoising, whereas before it was much more noisy. So down here on the bottom, you can see what kind of effect this has on the activation maps. So again, here before Nordic, this is percent signal change maps. And before the denoising, there was just a lot of false positive activation, a lot of noise. And after Nordic, a lot of this has been cleaned up, and we end up with mainly the activation being in the here down in the hand knob of the primary motor cortex, which is where we expected for this task, which was finger tapping in this case. So what can we use Nordic for? Well, we can use it for instance to improve the robustness of our statistics, increase the t-values and more robust parameter estimates. We could use it to, for instance, shorten our scan time, so we don't need as many trials. It could also help enabling of lower CNR paradigms. So if we move outside of the primary brain areas, then maybe this thermal noise removal would be helpful and increase the CNR, which is kind of low in these paradigms. And then it may also help enabling of smaller RIs, so we're not that reliant on averaging across a large region of the brain to get the sufficient SNR. So since Nordic is a thermal removal technique, it will obviously be more and more helpful and useful when the thermal noise becomes more and more dominant. So that will be at higher resolutions, shorter TRs, and at lower field strengths. So it would make a lot of sense in the context of laminar fMRI, for example. Okay, so Nordic has been validated quite extensively for gradient echo bold data, where it has proven quite successful. And there has also been some cases where Nordic was applied to VASO data, and I'll quickly go through these. And this is a case from Renzo's, one of his recent papers. And basically, if Nordic just removes thermal noise, then we would expect that the set activation maps, that the set values will increase in the activated part of the brain, and then the false positive activation around the other part of the brain should kind of go down, and we should get more clean images. But here it seems to be kind of the opposite effect. So after Nordic, we get a lot of spurious activation, a lot of false positive activation, especially these large patches here outside of the brain. And also we can see that Nordic seems to change the magnitude of the response. So the percent signal changes seem to here decrease in the deeper layers here, and it seems to increase in the superficial layers. So something seems to go wrong, and it could, for instance, be due to, in this case, they used an old version of Nordic where the thresholding value was scaled in a wrong way, which has been updated in the recent GitHub versions. And it could also be due to the way Nordic was implemented, which I will get more into in a second. So here we have another case from Akbari et al., where again we see it seems like after Nordic, which is over here, the laminar profiles after Nordic compared to before Nordic, that the magnitude of response seems to increase a lot. So the percent signal changes increase. And if Nordic only removes thermal noise, then this should not really be the case. The t-values are supposed to increase, but the percent signal changes should be left unaltered. Then here is a case from Pisuti et al., where we look at the TSNR maps, and clearly Nordic seems to increase the TSNR, but we also have these funny stripes here, which could be just due to the face images not being reconstructed in the proper way. And then finally here we have a case from Oliveira et al., where nothing particular seemed to go wrong. The data, there was no clear stuff going wrong, but they didn't report any validation, so there was no comparison with no Nordic, and also they didn't mention whether they found something that was removed from the data that was not just thermal noise. So this is just to say that Nordic has been applied to VASO data also very recently, but something funny seems to go on in a lot of cases, and it's not really clear how Nordic should be properly implemented for VASO data. So I think it would be valuable with some extra validation.
Semi-stupid question.
Yeah.
A lot of the Nordic papers are just looking at contrast to noise or TSNR improvements. Has anyone looked at this stuff on non-VASO data? Like, are we seeing changes in response relationships or contrast differences?
Yeah, so for instance, Victor Pfaffenroth, he has a recent abstract for ISMRM where he also found that, especially towards the superficial layers in gradient epipole, the percent signal changes there was a bias, so they found smaller percent signal changes after Nordic compared to before, but it was quite a small effect. And also in the data that I had from 3 Tesla with gradient epipole, we kind of saw the same effect, but again, it was quite small.
I just remember you in advance you talked about recording this. Should we record?
I'm doing.
Oh, you are recording.
Yeah.
Good.
And if you move your mouse real quick, then the black screen goes away. And aside of Victor Pfaffenroth, also Logan Dow from the Nordic group does those tests, Federico De Martino, and also Kendrick Kay has a more kind of theoretical overview paper talking about, like, in principle what it should do with less empirical kind of tests for layers. But there is a lot for kind of bold or conventional contrast, not like very little about VASO.
You sure you're recording? Because I should see a button. I should see a notice.
Screen capturing.
Oh, you're screen capturing. Okay, good.
Including Luca's paper, the original paper was wonderful.
Yes. All right, so this motivated the work that we have been doing here for the past 4 weeks. So where the purpose was to test Nordic across a wide parameter space to kind of get a feeling of how should we implement Nordic for this type of VASO data, and also what are the benefits of doing so, and how and when can it go wrong. So to be specific, the first thing that we looked into was whether we should do Nordic on the combined null and not null time series as shown here, or if we should instead separate them first and then do the denoising individually on null and not null time series. Then we also looked at whether we should use an appended noise volume. So this is typically a volume that is acquired after the functional run with the exact same sequence, the exact same readout, but where the RF pulse has been set to 0, so we don't measure any signal. We basically just record the thermal noise, and then this image can be used to estimate what is the thermal noise level, which is then used to set the threshold that determines which components are being removed. The alternative to this would be to just not give Nordic a noise volume, and then Nordic estimates the noise level directly from the data using another PCA-based method called MP-PCA. And I think theoretically, maybe it makes more sense to just use this volume where we can kind of directly measure what is the thermal noise level. But we wanted to measure to like test here empirically if it really makes a difference. Also because that would make this one is more the lower one without the noise volume is more easily implementable for many VASO users, especially those who used the older versions where the noise volume was not automatically recorded, right? But that has been implemented in the newer versions. Okay, so then finally we wanted to look at whether we should use the full complex value data set or just only the magnitude only data. And I think again theoretically it makes more sense to use the full complex value data and has been, I think, recommended for gradient equibold data because it has the advantages both that we have more information when we also include the phase, but also because one of the assumptions in Nordic is that the thermal noise distribution is identical across space, and that is better fulfilled for the full complex value data compared to magnitude only. But it is not clear whether this is also the case that this should be the best way to apply it in VASO, because the phase information is just different in VASO, which you can see here if I flip back and forth between the null and the not null phase images. Then in VASO, the CSF phase, the phase in CSF may be negative because of the inversion pulse, and so there could be some differences. All right. So the data that we used to test this was a 3T multi-echo VASO data set from Renzo's recent paper here, which had 6 runs that were 12 minutes duration each, and it had around 0.9 millimeter isotropic resolution. And it was a block-designed paradigm with simultaneous finger tapping and visual stimulation. So we defined a large RI here, which covered both visual cortex and the somatomotor cortex. And this is just one slice, so it did extend into multiple slices, and it was quite a large RI consisting of around 7,000 voxels. Then we also defined another smaller RI, which was just in a small subsection of V1, which was used to extract laminar profiles. And the reason for using this data set was kind of twofold. One is that we wanted a data set with kind of small CNR, because that's the domain where Nordic might be most useful, but also because that is where it's most challenged in some sense, because ultimately the denoising performance on Nordic will come down to what is this CNR of the data originally. So basically the thought process was that if it works here for this case where it's 3T, it is VASO, it is sub-millimeter resolution, so fairly low CNR to begin with, then it should work across a wide range of studies. And also this simultaneous motor stimulation and visual stimulation does activate quite a large area of the brain, which allowed us to make this large RI, so we could average across many voxels and get a pretty good ground truth estimate at the single trial level, which will be important in a second. So now let's look at the results. So the first thing that we looked into was just the denoising performance. So how much noise is being removed for these different versions, for which we used TSNR as kind of a proxy. So the way it's structured here is that we have these 9 different versions. We have no Nordic over here, and then we have the versions with a noise volume, without a noise volume, the combined versions, and the separate versions. And you do see my mouse, right?
Yeah, I think online they don't.
They don't?
No.
Oh.
Maybe that's the
If you use the pointer, go to the tiny pen on the corner, Yeah, and say
Laser
laser pointer, usually that helps a little.
Yes,
Yes,
yes.
yes.
Okay, sorry about that. So this is the way it's structured, and then if I switch to the next slide, then this would be the magnitude data. And this, the first one here is the complex data.
That's I was curious, so looking at the TSNR is interesting, but I was curious if the baseline values actually change with the application of Nordic. Like, so is it that there's less noise, but the baseline is identical, or does it change both the amount of noise and the baseline?
And the signal, baseline signal. Yeah, but I think we will get into that in a few slides. I'll show. But basically, if I switch back and forth between these two versions here, then I think in all these 8 different Nordic cases, it does seem like we get quite a nice of a TSNR improvement, and compared to the no Nordic one here to the left, and 2 of them really seems to stand out, which are the two ones over here to the left. So that's the complex valued versions with a noise volume, and it does not really seem like it makes a difference if it's combined or separately denoised. If we then look at the magnitude only versions, then there are these kind of weird patches here of very large TSNR values, which we do believe could be due to 2 different reasons. So one of them is that, as I mentioned before, for the magnitude only versions, we might, or we probably violate the assumption of identically distributed thermal noise, especially outside of the brain, where the thermal noise will have a Riccian distribution and not a Gaussian distribution. And that is not the case for the complex valued versions. And here, these patches also seem to decrease to a large extent. So that might be one explanation. The other if this was the only explanation, then we would also expect that this should happen maybe more towards the corners, also more uniformly outside of the brain. But it has this structure. And I think the G factor might help us explain this. So here, this is from another data set where we also had the G factor directly computed from the scanner using the graph weights. And there we see that it has these very sharp edges in the G factor, but it is smooth inside of the brain. Whereas for the G factor that is estimated in Nordic in the versions that we have been using, these sharp edges does not seem to be captured. So they have these very blurry edges around the brain, meaning that when we use the G factor to normalize the data to get homogeneous noise across the whole image, then this probably goes wrong if the G factor map is not strictly correct outside of the brain. And that could also help explain why then we would get wrong noise estimates, and that could make the denoising break down, so to speak. Okay, so now the t-value maps, these were computed by, first we estimated the percent signal change for each single trial, of which we had 72, and then we computed the t-values across those trials. And this was to account for the potential bias that could be implemented if we use the normal standard general linear model framework, where the degrees of freedom is expected to be changed when we use Nordic and remove components from the data. But again, if I flip back and forth here between the magnitude and complex versions, I think, again, in accordance with the TSNR maps, these complex valued versions to the left with a noise volume seems to stand out. So they seem to provide stronger t-values around the region of interest. So this is just only based, if we only base the conclusion on which implementation is the best one based on which one removes most thermal noise, then these 2 here seems to be the ones standing out. But then we looked into whether Nordic also, how will it, or the different versions in Nordic keep the signal intact. So the way we did it is that we plotted the percent signal change for each single trial after averaging across all the voxels within this large RI. So we should basically have averaged out all of the thermal noise. And so if we when we compare no Nordic and Nordic, if Nordic literally only removes thermal noise, then I would expect all of these lines here to be completely flat. But again, if I switch back and forth between the different versions, then I think one clear pattern is that all these versions up here, the combined versions, they do seem to have a clear bias towards reduced percent signal changes. If we then look at the lower row, it does seem to get a little bit better. And I think especially this version here, which is the magnitude only with a noise volume and where the denoising was performed separately, I think seems to be the best one. So that seems to preserve the signal quite well. There might be a little bias, but mostly the lines are horizontal, and it's more random if it goes up or down a little bit. So why is it that we do see this, that the combined versions seems to have a problem and seems to have a bias? One explanation might be that even though we have twice the number of dimensions when we do combine the time series, because we have twice the number of volumes, we may get the problem that we more than double the number of signal components, so the number of components that are needed to describe the signal, because maybe the signal just becomes more complex due to different interactions between the VASO and the bold time series. So we get an overall much more complex signal that is needed to be described. And when we do have more signal components, it can become more difficult for the PCA to distinguish signal and noise components. Okay, so then we looked into whether Nordic altered the temporal structure of the data. And the way we did this is that we took these single trial estimates, again after averaging across all the voxels, and then we this time just plotted them as a time series. And what is interesting to me is that there may be this small bias that maybe there is a small reduction in the overall percent signal change after denoising, which is the red line, but the true variability across trials seems to be kept intact. So the variability that is not just explained by thermal noise. Then and this is for the version that we like the best from the previous plot. If we then look at the version which seemed to have the problem, the largest problem in terms of removing signal, then it seems we can clearly see this overall bias in the percent signal changes. But even for this version, still it seems like the majority of the true variance across trials seems to be kept more or less intact, which I think is important.
Yeah, it's interesting. Kind of curiosity, why this entire time series has percent signal change above 0? What's it in reference to?
This is just it's the inverted basal activation. So it's the average of all the on blocks where they were doing the task minus the average of all the resting blocks, and then normalized by.
Okay, yeah. I thought these were 10%. No.
Yeah, each point here is the percent signal change for one trial. Okay, then we look into whether Nordic alters the laminar profile. And again, this was for the version that we liked the best from before. We kept the signal mostly intact. And I think these laminar profiles, they are both identical in terms of the shape. And also it seems like the magnitude of the response is also identical within error. So that is quite nice that we can kind of obtain the same laminar profile after denoising, but just with smaller error bars. So we could, for instance, get the same profile, but just using much less trials. And also the fact that the shape is kind of kept intact suggests that Nordic does not induce any harmful blurring, because then we would expect the red profile to maybe be more flat, or at least to change its shape compared to the blue one. Okay, so then finally we looked into the trade-off between noise removal and signal removal. So this has been nicely discussed by Kendrick Kay in one of his recent papers, where with most denoising methods, we do have the trade-off that we may remove a lot of noise, but we also have the risk of introducing bias as I kind of showed you before also. And I think this figure quite nicely illustrates this point. So Nordic has the flexibility in the sense that you can change this threshold that determines which principal components are being removed, and you can scale this threshold by an argument called factor error. So if we increase the threshold, we will start removing more components. And the scaling factor of 1 would be the default, and then you can see that when we start increasing this scaling factor, we do get more robust activation. This is again T-maps. We do get more robust activation, and here when we really push it, we get much more robust activation, even here up in the sensory motor cortex, which was not that visible in these other cases. But as you can also see down here, the more we push this threshold, the more noise or the more signal we also start to remove. So we get a larger and larger bias. And I think the fact that we already do see some signal removal for this case here, which is even more conservative than the default, so we remove less components. Even here, we do see some signal loss. It is small, but it is significant. And that kind of suggests that I think the reason why is that we will, due to thermal noise, all of the principal components will in some sense be corrupted both by thermal noise, but the signal will also spread to all of the components, meaning that even as we're removing just a few ones, we will inevitably end up removing signal. But the point is that in many cases, at least for the default setting, the amount of bias we're introducing and the degree of signal removal is probably more or less negligible, and maybe worth it when thinking about how much thermal noise we're also removing at the same time. So this is just a different way of kind of showing the same thing. So here we looked at the time series Nordic minus no Nordic, which kind of represents what is Nordic removing from the original data. And then we computed the activation map for this difference time series. And now it's not a percent signal change, it's just a delta, so it's just a raw difference, again, between the average of the on blocks minus the average of the resting blocks. And then we do see here that for the default case, it just looks like random noise as we want it to, but we can see that when we average across all the voxels, that there is some signal in this activation map of the difference. So we do remove some signal already here. And then clearly this just becomes worse when we increase the scaling factor, as also shown to the left, and we start to even see this activation or this signal directly in the activation map. And down here it becomes quite extreme when the scaling factor is 5.
Were these tests done with the full data? So these were complex?
No, this is all for the version that we like the best.
Okay.
So separate and magnitude only. Yeah. All right. So in conclusion, I think the version that we like the best was the separate one with noise volume and magnitude only, and maybe closely followed by the separate versions without a noise volume. But of course, it is important to mention that maybe we should probably not make too strong conclusions about which version is the best, since this is one subject, it's one experimental setup, and then maybe it could change a little bit for different cases. But the main message here is just that this particular version here seems to be a fairly safe way of implementing Nordic on VASO data, where we have quite minimal signal loss. We did not seem to alter the temporal structure in the data. The laminar profiles were identical with and without denoising, and we do get this increase in TSNR of about 2. So yeah, I think our results suggest that we can use Nordic also in VASO data, but that the implementation is quite important. And then we made a wrapper for this for how to implement Nordic on VASO data and made it available here on GitHub. And then yeah, thank you.
You look at I mean, maybe it doesn't work the same way I'm coming from the data. Have you looked at independent components that you're removing to see if when you're losing signal, it's just a few of them that are the problem, or you're losing the signal equally distributed across the whole set of components that you
Right. Yeah, I haven't looked specifically at the components we're removing, but we have been looking at again we looked at this difference time series, which represents what Nordic is removing, right?
No, I'm just thinking from the, if you could identify, for example, it's just a few, then you might better understand what's going on.
Right.
Or put an extra, reasoning in the program to care for them. If it's equally distributed across the whole thing, then
Right,
it's a part of the problem.
Yeah, that's a good point, but I actually don't know how to see the components that Nordic is removing. Maybe there is an option to
I
do
mean,
some
it's not
measurement.
trivial because it's a patch wise, right? And they overlap the different patches. So in each patch, you have your
But
component.
you don't have a map that is like.
No,
okay,
it's not like for the 40 time series, it does the PCA, it really does it in these patches, which I think is a very effective way in Nordic, that it kind of making it small in space, and like it forces it to use more time dimensions than space dimensions. But then on the other hand, for each voxel, you don't have kind of one component, but you have the different patches that overlap.
I think the underlying always big question is Nordic doing what it claims to be doing? I was just thinking, as you were presenting, I was thinking of another way that might be pretty practical to test. So if you go back to your TSNR maps, the 4 methods.
Yes.
If not any of these. So Nordic is just, in theory, going to be just removing the thermal line. Actually, I think the next one after this one. Yeah, so Nordic is just removing the thermal lines. So that means that if you correlate no Nordic with any of those 4, the correlation should always be positive. And the magnitude of the correlation should scale perfectly with the magnitude of the TSNR. So the more you improve TSNR, the stronger, the weaker the correlation, actually, I guess, because you're changing, you're removing more noise from one than the other. So they're going to be a little bit more different scaling with TSNR. And that might be a way to sort of, instead of looking at the ROIs, you can look at the whole map and say, or am I, is everything positive, and is it essentially scaling perfectly with the amount of noise I'm removing? So kind of like an ISC, so intervoxel, voxel to voxel correlation on no Nordic to the others.
Right.
I was originally thinking of just looking at the width noise vol combined separate. They look so similar that I was just thinking just the correlation between the two, or is it giving you effectively an identical time series, or are there differences? So I think those are 2 ways of thinking about it. Because in theory, your true time series should be perfectly the same, and then everything that's removed is going to be purely Gaussian. I mean, that's not perfectly true, but that this might be a way to sort of spatially map where and how those violations happen.
Right.
You just brainstorming here.
Torben had a question. If you unmute, I'm not sure if we're going to hear you.
You should be able to.
So now I'm unmuted. Can you
Yes.
hear me? Good. I have a question regarding the amplitude. So I remember from your previous work, Lasse, that you found Nordic to decrease the amplitude in the profiles. Yet, if you look at some of the percent signal change plots, there was like a conflict in that the profiles were reduced, but there was another one that was increased. So yeah, so this one here. So
Right.
So on the right plot, the no Nordic version has the smallest amplitude.
Yes.
Nordic has the highest.
Yes.
And then if you go to the figure on the left, maybe I'm confused by the complex figure, because the other one is magnitude, but there it seems to go the other way around.
Yes, and I think in all of the versions, if there is any bias, it seems like it's going downwards. So there's lower percent signal changes after Nordic compared to before. but yeah, that is not what we see here in this profile. And maybe so these plots here are made across the full ROI, a lot of visual cortex, a lot of sensory motor cortex, and this is just a very small region of V1. So maybe it does vary a little bit across space, I guess.
Maybe you can show the maps again of the factor error where you on the few more slides there, where you see on the right that sometimes it's positive and negative, whereas on the graph you see then on average it's always a reduction, but there are always voxels in some south side that kind of go the other way around.
Right.
It could, however, be enormous amount of benefits anyway. I would like to see this particular figure with a constant number of super threshold voxels, because that's I think a good way to demonstrate whether you use the increased sensitivity to also increase the specificity, or whether you could just turn up and down the threshold instead.
Right. Yeah.
And then I think that you said that you made average T maps. Don't you mean that you did a second level analysis of the beta images?
Yeah. So to compute these T values, we did a second level analysis of the percent signal change.
It's not the average of the T maps, but rather it's like a second level analysis on individual trials, and that is in order to avoid the temporal correlation. That actually relates to I don't know if it's Daniel who is on the screen, to your question regarding the correlation. It may be different from in VASO, where the TR is long than it is in ordinary gold, where the TR can be kept slightly shorter. But there is a potential issue of increased coloring of the noise. Of course, the noise is always colored, the physiological noise, but if it's significantly undersampled or aliased, then it may look white. I should say it another way. If you sample sufficiently fast, then you can get in the situation where the white noise is dominant before Nordic, and then after applying Nordic, then you suddenly very clearly see peaks corresponding to respiration and cardiac pulsation and so on. Meaning that it can be a possibly more complex relationship when you're doing the correlation, because the noise is not nice after Nordic. The remaining noise is only physiological.
I have a question about the laminar profiles.
Yes.
What are the units? You have it labeled as delta, but
yes. So this is the same as we did for these different ones over here. So it's just here we just don't normalize by the average of the resting blocks. And the reason why was that we were worried that here towards CSF, we might be very close to zero. So if the signal is close to zero, so if we are dividing by something close to zero, then it kind of explodes, right? So that's why we avoided to compute percent signal changes here, but we just look directly at the raw difference between average of on blocks versus average of resting blocks.
And it is still VASO, so it's inherently normalized of blood mounting versus not mounting. So it's in units of set magnetization, basically.
okay.
And then I don't think I actually answered your first question with the TSNR, but I think I haven't evaluated this statistically or anything. But if I just look at the raw time series with and without Nordic, I think it looks like it's just thermal noise, but the kind of the baseline level seems to be the same. So that the TSNR improvement seems to mainly come from thermal noise removal.
So that's, yeah, I guess that's interesting because if I remember correctly, Nordic calculates the baseline as part of the first principal component, right?
Not sure about that. I don't know.
As in, like, in each of your patches, there's no mean removal before and you add it back in. It's like part of the analysis, but okay.
Yeah, I don't know. I would have thought that it would remove the mean to begin with, since it is PCA, right? But I'm not 100% sure how it is in Nordic.
Okay. And have you done any testing on the other parameters that Nordic is capable of?
Like pet size and
yeah.
no, not extensively. We did have the concern that one of the reasons for why the combined one seems to be a problem, that maybe it's because the default pet size in Nordic is computed based on the time series length, and that is doubled in the combined versions. So maybe the problem could be due to the pet sizes just being too large in those versions. So I did try to for the combined version use a smaller pet size in one case, but the problem was still there. So that's the only thing I have done with this specific parameter, and we haven't played around with other.
But the patch sizes were kept equal in all of the
in the other
analyses.
versions, yes. Yeah.
Yeah, it's always interesting because when we look at these TSNR maps, they clearly have block structure in areas where you get where you could be potentially increasing the TSNR within one patch, which is, yeah, it tells you that it's doing something, which is good.
Yeah.
But what it's doing is potentially an open question.
Right.
Do you have any ideas for why the increase in TSNR outside of the brain is so lateralized? Do you think that has to do with the G factor maps folding over in the phase encoding direction, or?
You mean why they are left and right and not up and down?
Yeah, or just everywhere, or why sometimes you get corner artifacts, or
What was the phase encoding direction in this?
It was AP here.
Okay.
So I think it's more the brain in this field of view is wider, so it basically touches the border on left-right more. And the way how, like, depending on the patch size in which it estimates the G factor, like you cannot have a G factor border or change within the patch. So it's always kind of more blurrier in the G factor estimation within the master implementation of Nordic as opposed to true G factor. So always when you have the border of the brain, then I think there the noise threshold estimation might fail, which is kind of happening there. And but there you also have it right at the border of the field of view, and we don't have this in the head feed direction. I guess the phase encoding might make sense because there's always a bit of ghosting, like that the signal is never really zero. Before, like in front and back of the brain, but left and right, there is no ghost whatsoever, right? Because so I think it would make sense that it's a combination of those, right? The G factor misinterpretation while having Reichen noise, while assuming it's Gaussian, zero mean, and on top of that also having kind of true thermal noise in those patches and not ghost, which would introduce a bit of signal still.
Yes. And it is definitely related to the patch size. I tried in the version where I tried to make the patch size smaller, it seemed to go away to some extent.
Okay, that's interesting. So one last kind of implementation question. I think you mentioned the number of components in the time domain and the spatial domain. I thought I was under the impression that they were using an SVD solver, and then it wouldn't be possible to have different number of components in each of those domains. Am I misunderstanding something, or?
I don't know anything about the SVD solver. I was just thinking about the number of kind of information you give Nordic to do the PCA. And if you have larger patch sizes with the same time domain, then you have more degrees of freedom in space. Whereas when you make it, let's say, a tiny voxel, then you can only do PCA across time.
Mhm.
Or make it 9 by like 3 by 3, then
No, that's helpful. Yeah. Okay.
one more question from Torben.
I wonder if a possible solution for the combined would be to just run it on half the time series or in chunks of half a time series, but then merge the time series afterwards.
Yes.
Because that's maybe more similar to what you do when you do it separate.
Yeah, that makes sense. But I guess the problem, normally it would be a good thing that we do have longer time series, right? I mean, the reason why my concern with this would just be that the patch size is scaled by this time series duration.
Exactly.
In default.
And you want to compare the different approaches rather than comparing different patch sizes, because otherwise you just adjust.
Yeah, makes sense.
So I think that could possibly be a solution.
Yes.
Of course, then there's the issue of the concatenation, whether that is successful, but then you still only have one of these in the combined, whereas you would have lots of them. One of them in. No, you would have one of them in each. That would work. Yeah. So you have several in the separate. That's a good deal. I don't know. But split them in run them in first and second half, possibly.
All right, if there are no further questions, I want to let people in the room know that there will be cake upstairs in the meeting room. Please join us.
That's good.
All right. Thank you.